My name is Rui. I'm from the Imperial College in London, and I think Emma from Edinburgh Napier is also on the call. So I'm going to talk about our paper in which we presented this algorithm called WILDA, which stands for Wide Learning of Diverse Architectures, and we use it to classify large data sets. So I will introduce the concept and the motivation behind it, and then I will talk about the actual algorithm in all its three phases, and I will talk about experimental results and further work afterwards. So when we talk about deep learning, we basically talk about these very complex models, which scale mostly in a vertical fashion, using many layers. And conversely, wide learning promotes diverse feature extraction in parallel. So this is a type of scaling that is mostly horizontal. So the idea is to extract a certain set of features and then aggregate them in some way to produce the final output. So there is plenty of motivation to go wider instead of going deeper. So for instance, wide networks have been found to scale better. And that means that increasing width by a small factor yields better results than increasing depth by a much larger factor. So one example is this paper about wide residual networks, in which they verified this. So increasing width by a very small factor was basically leading to better results than very, very deep networks. The other motivating factor is that there is a pressing concern in AI research about the inequality of access to computational resources. Realistically, it is very hard for universities nowadays to compete with the results achieved by big tech companies, the likes of Google, for instance. And so going wide instead of going deep, adopting methods of wide learning might help mitigate this inequality. There is this paper that I recommend about the compute divide in AI. It proposes some solutions, mostly political solutions, but it talks about this issue. So moving on to the actual algorithm, it has three phases. The first phase is the feature extraction phase, in which we have a set of shallow neural networks, each of them extracting a feature vector from the input. And then a feature selection phase, in which we select a subset of these networks to actually produce the final feature vector that we want. And then a classification phase in which we feed these features into a shallow model that will actually output the final results. So again, just to reiterate, this algorithm uses a three-phase approach. The first phase is the feature extraction phase. Like I said, it involves a set of shallow neural networks, and it uses a distributed evolutionary algorithm to do that. So each of these networks will extract a low-dimensional feature from the input data. Then a feature selection phase, where we select a final subset of features, and a final classification phase, where we train a single shallow neural network using the selected features to produce the final output. So we know that the performance of an ensemble is often better than that of its individual members if they are sufficiently diverse. This is what the literature tells us. And on this paper, we have focused on architectural diversity. So our hypothesis is that if you have diverse architectures, then you will probably have diverse features being extracted from the data. And so we use a quality diversity algorithm to evolve the neural networks, because this class of algorithms is known to deliver diverse, but at the same time, high quality solutions. And the quality diversity algorithm that we use is called map elites. So this is an algorithm that enables the choice of a set of diversity features and the range of their values. So a single run will return a set of solutions. These solutions are mapped to a multidimensional archive, which is defined by these diversity features that we have selected. And in each cell of this archive, we store the best solution according to a fitness function, which has the respective diversity features. So this is the original algorithm. It's taken directly from the paper that was proposed. So basically, this algorithm works by initializing a random population, and then at each iteration, you select a random solution from this archive. You produce a new solution by using a random variation operation, such as crossover or mutation that I'm going to talk about in the next few slides. Then you extract a feature descriptor from this solution, you calculate its performance, and then you see where this solution will be in the archive according to the feature descriptor. And if there is nothing there, or if its performance is better than the performance of whatever is there, then you replace it in the archive. So it's a very simple algorithm. And it can be used to reduce a very high dimensional space into a smaller dimensional space that is defined by the set of diversity features that we select. The set of diversity features is, of course, domain dependent. So in our case, we consider the number of convolutional layers in the network, also the number of dense layers, and the maximum size of any dense layer. So it's a three-dimensional space. And here is an example of basically how we map a neural network onto this three-dimensional archive. We basically just extract these features from the network. Again, the number of convolutional layers, the number of dense layers, and the maximum size of any dense layer. That produces a mapping on this three-dimensional space. So our fitness function is the performance accuracy on a validation data set. And before that, each network is trained on a subset of the training data with a standard stochastic gradient descent procedure. So our variation operations are, like I said before, crossover mutation. So crossover just takes two networks and it swaps their layers at random locations, as you can see here. And mutation basically adds or removes a layer at a certain a random position in the network, as you can see here. Oops. So this algorithm, or this first phase, feature extraction phase, is distributed across multiple nodes. So each node runs the map ellipse algorithm independently, and then the results are combined in the next phase, which is the feature selection phase. So in this feature selection phase, we merge the archives that are produced by the multiple nodes into a single archive. We use one of two strategies. The first one we call merge without overlap. So each cell will contain only the single best neural network in the same cell found across all individual archives. And the second strategy we call merge with overlap. And each cell will contain basically all corresponding neural networks across the individual archives. And then after merging the archives, we truncate them by taking the n best neural networks. That means the ones with highest validation set accuracy. And this will be the final ensemble. And then given a certain input vector, a feature vector of fixed size is extracted from each network. And we define this as the output of the final hidden dense layer. So as you can see here, given a certain input, what we call, or the feature vector that we extract is the output of this final dense layer, and it has fixed size across all networks. Sorry, okay. So after we've extracted these feature vectors, we concatenate them in the classification phase, and then we train a shallow neural network with stochastic gradient descent, and this one will solve the task directly. So it will use the concatenated feature vectors as input and produce the final output. So this is what is shown here. Each of these feature vectors is extracted by each neural network in the ensemble. And then we feed them, we concatenate them, and we feed them onto this shallow model in order to produce the final output. So I'm going to talk about some experimental results. So we've carried out experiments on the MNIST and CIFAR 10 datasets. So the goal of these experiments has been to, firstly, to compare the results with the baseline. So the baseline that we've selected is basically the single best individual model found during the first feature extraction phase. So if you recall, each node is running map-elites, finding a set of neural networks, and each of them has a fitness score, which is the validation set accuracy. So we just select the best architecture that is found and compare its accuracy with that of the ensembles that are generated by WILDA. We also compare both merge strategies that I spoke about, and we investigate the role of architectural diversity and also the influence of ensemble size. So when comparing to the baseline, we found out that WILDA significantly outperforms the baseline using either merge strategy. So this means there is a performance gain when using an ensemble compared to the best individual neural network, which seems like a fair baseline for comparing an ensemble against. Basically, we can obtain reasonable performance with WILDA without using vast amounts of computational power, without fine-tuning the networks with expert knowledge too much. When we compared both merge strategies, so the one that uses overlap and the one that does not use overlap, we have observed very similar results. So there is no statistically significant difference between these two methods. There are several reasons why this is the case. There could be several reasons why this is the case. We think that maybe each node might be finding high-performing neural networks in different regions of their archives. So when you merge them, they will not actually overlap. And also, it's possible that when more than one network is mapped to the same cell in the final archive, that they are still significantly diverse. And so we still preserve some architectural diversity in this process. Then we investigated the role of architectural diversity. So we compared the architecturally diverse ensembles that are evolved by our algorithm with two kinds of ensembles where the architecture is fixed, and so diversity results only from training on different subsets of the data. The first kind of these such ensembles is ensembles made of instances of the best architecture found during the feature extraction phase. And then we also compared these with ensembles of instances of the worst architecture found. So perhaps unsurprisingly, the ensembles with the best architecture outperformed the ensembles with the worst architecture. But more interestingly, the ensembles that were generated by WILDA outperformed both kinds of ensembles with fixed architectures. So this means that architectural diversity is leading to better performance. And so our hypothesis is that it is very likely correlated with error diversity, which we know is important in ensembles. And this correlated itself with ensemble performance. We then investigated the influence of ensemble size. So basically in the feature selection phase, I said that we take the n best neural networks. Well, this number n is a parameter setting, and observations on both data sets suggest that the value for this parameter that results in optimal performance is probably domain dependent, and the conclusion is that it must be fine-tuned to the problem being tackled. So this is an example of how the feature extraction phase using mappy leads can be used to illuminate the search space of architectures. Note that only 2 of the 3 diversity features are shown here. But basically, the way we interpreted this, the way we can interpret this is by looking at the color shading, which indicates the accuracy of the best network found with that set of diversity features. I'm just going to talk a bit about further work where this has been going in the meantime. I must say this approach has been considerably improved on in our Gecko 2021 paper, which we just published, which is going to be published. It was just accepted, using novelty search to explicitly create diversity in ensembles of classifiers. So we now focus explicitly on error diversity, so the behavioral diversity of the ensemble members. And we're now using novelty search to evolve ensembles. And the nice thing about this paper is that we are selecting for diversity, but not for accuracy explicitly. And we propose some new diversity metrics, which have led to better results than those found in the literature. And we are now generalizing this new procedure to also use novelty search with local competition. So this is another quality diversity algorithm. So right now, we don't just look at diversity, we also look at accuracy explicitly. And we are using surrogate models to estimate both the distance between the behaviors of models, because this is something we need for the novelty search, and also the accuracy, which is what we need when using local competition. So this enables the exploration of a larger search space of architectures, and it has already resulted in better accuracy, in better final ensemble accuracy. We're also testing new diversity metrics. So I'm gonna leave it there. Thank you for your attention.
Rui, thanks a lot for your presentation. Lots of fascinating ideas in the end. So apparently we have at least 1 question. So Pedro, please go ahead. Oh, lots of questions. Pedro Carvalho, you first, I believe.
Hello, can you hear me?
Yes, perfectly.
Thank you for your presentation, Rui. Before I move on to the question, you mentioned at the start that one of the motivations of your work was to address this problem with the inequality of access to computational resources between universities and big companies. Could you speak a little about how long and how computationally intensive is the process of finding these networks that end up comprising the ensembles? Because I would think that this is also an expensive process.
Yeah, you're quite right. It isn't a cheap process. Yeah, that I talked about this here. Obviously, the way we were doing this in the beginning, at each iteration, in order to score the networks, we had to train each network with a gradient descent procedure, and then get its classification accuracy on a validation data set. Obviously, the training part was very expensive, and this is why in current work we are using surrogate models. So we have a set of pre-trained neural networks, and then we basically train a random forest model to guess the accuracy given architecture descriptors, to guess both the accuracy that can be achieved by a certain architecture, and also the distance between the behaviors of each architecture. Because that essentially eliminates that step, that very expensive step of having to train the networks. And basically you only train them in the end after you have selected your final ensemble, then you train the ensemble and get the final result. But yes, in the beginning, it was also a pretty expensive step of training each neural network so that you could get a fitness score. Yeah, that's it. So the only difference is that it was distributed, and because it was distributed, it was slightly easier to handle than, and these were all shallow networks, so it was slightly easier to handle than having a very complex network, or maybe a smaller set of very complex networks. But yes, that was a good point.
Okay, thank you. I'm looking forward to seeing your future work as well.
Thank you.
Okay, thank you. So another question. So Ollie, please go ahead.
Yes, hi, can you hear me?
Yes.
Yeah, thank you very much for the presentation. I appreciate it. One question I had about the diversity aspects of this work. Certainly there has been a lot of work on diversity preservation in evolutionary computation. And I was wondering, did you try out, it seemed like you very quickly jumped to map elites and then to novelty search. Have you considered other types of diversity preservation methods in this work? I mean, for me, that would be quite interesting, I have to say, because diversity, of course, is very central in evolutionary computation. And what were the results if you tried out other methods? Like, other methods, I mean, niching methods from GAs, crowding methods, both from GAs and from GP and so on.
Yeah, that sounds very interesting. So yes, the original idea to use MapElite was because we could basically take these diversity features that were, we could very simply select a set of diversity features by looking at the architecture of the networks. So we focus on architectural diversity. And then the point of using novelty search is because we can just plug in different diversity metrics that are proposed in the literature, and others that we propose ourselves. But yes, I think you're very right that there is plenty of scope for improving on these results and studying the issue of diversity. Oh yeah, we're very interested in that particular subject. And thank you for your suggestions.
Great, thank you very much.
Okay, Igor, one final question. So we still have time.
Okay, so you use a shallow network after feature selection. So did you consider maybe to use another classifier like random forest or support vector machines to make this final step?
We could do, yeah, that would be interesting to test. We haven't tried that out.
Okay,
Yeah,
I have supervised one master thesis, and the results with only one large network were worse than from the network together with support vector machine or random forest after this network. So maybe it's also, maybe I can try it.
Yeah, definitely. And also because, random forest regressors are very easy to use off the shelf. There are many implementations, and yeah, definitely. it's definitely worth trying. Actually, the surrogate models that we're using right now, they are random forest regressors.
Ah,
So, yeah.
okay. Okay, all right, thank you.
But thank you for your suggestion as well. Thank you.
Okay, thanks for your presentation, Rui.